introduction, guys. And thank you for this nice opportunity to present my work. And today, let's talk about the topic self-healing and transparent ionic conductive hydrogels with multi-sensing capabilities for wearable sensors. So before we talk about the topic, let's first see the research of our group. I work in the group of Professor Pedro Fadim. Our group focuses on the study of biopolymer and polysaccharides such as lignin, proline, dextrin, calcin, etc., and also ship them into high value-added products, where the utilization of these products center on the personal care, functional therapeutics, and functional prevention. Also, we welcome visiting students from other universities, and we look forward to meeting you at KULeuven. So let's move on to the background of wearable sensors. Conventionally, the wearable sensors are mainly based on semiconductors and metals. As we all know, these kinds of materials are rigid, brittle, and also with high modulus. So this means these materials cannot compatible with our body greatly and may lose some small deformation and tiny information from human body. So afterwards, researchers have used the PDMS as flexible materials, where even the flexibility but the stretchability is quite small, such as the stretchability normally less than 5%, and also PDMS lacks the functionalities. So we think about some new materials to tackle these limitations. Well, so recently, conductive hydrogels have received lots of interest in wearable sensors because conductive hydrogel possess some unique properties like flexibility, skin-like modulus, stretchability, and if we design the hydrogels carefully, we can use hydrogels with some multi-functionalities like self-healing, self-adhesive. When conductive hydrogels are exposed to different external stimuli, the resistance of conductive hydrogels will be changed. So in this way, the external stimuli could be quantified, and hence we can use the conductive hydrogel wearable sensors to monitor the health information from human body and provide information like heart rate, breathing rate, temperature variation, etc. Where, however, if we look at the conductive hydrogels, we can see the conventional conductive hydrogels are normally monosensing. That means this kind of conductive hydrogels can only respond to one stimuli, such as respond to mechanical strain or only temperature. Also, these kinds of conductive hydrogels will permanently suffer from the permanent function loss if we damage the hydrogel. And many of the conductive hydrogels are non-transparent. That means the interface between the hydrogels and the substrate is not visualized. So if we think about if we visualize the interface, we can get more information from the interface. So recently, there is a new trend that we develop some new materials with multi-sensing capabilities and also with faster and autonomous self-healing ability. And also, if we select some desired materials, the conductive hydrogels will be highly transparent. So in this work, we use PVA and proline as raw materials. As we know, PVA is a typical biocompatible materials for hydrogel preparation. The adjacent hydroxy group on PVA can react with borax to form borate ester bonds, and thus providing the self-healing ability. However, the PVA self-healing hydrogels suffer from some limitations. If we use a high concentration of borax, we can get a mechanically strong PV self-healing hydrogels, but the hydrogel will be brittle. If we use less borax, the PV hydrogels will be flexible, but the mechanical properties is not good enough. So researchers have introduced some biopolymers or polysaccharides to enhance the mechanical properties, such as we use calcium, cellulose, and their derivatives. Even though the transparency of the PV self-healing hydrogels will be largely sacrificed. So compared to these materials that we mentioned, like calcium cellulose, here we use KULeuven. Because KULeuven has high water solubility and it can form transparent solution in water. So in this way, we envision that KULeuven can enhance the mechanical properties and also keep the high transparency of PVA self-healing hydrogels. So in this work, we aim to prepare PVA KULeuven and borax ionic conductive hydrogels with good mechanical properties and also with multi-sensing capabilities, fast and autonomous self-healing, and high transparency. Well, let's move on to the preparation procedure. So first, we prepare PV and KULeuven mixture, and then we add borax solution, and then we stir it very quickly. After cooling down the mixture to room temperature, we can get the hydrogels. As we can see here, the objects after the hydrogels are visible, and the hydrogels are highly transparent. So let's see the gelation mechanism first. Here it involves some steps. First, it involves the dissociation of borax. Borax dissociates into sodium ions and borate ions, and then the borate ions can react with the hydroxy group on PVA and form the borate ester bonds. Besides, the hydroxy group on KULeuven and the hydroxy group on PVA can form the hydrogen bonding. There's a combination of hydrogen bonding and borate characterized by FTIR. As mentioned before, the purpose of a KULeuven is to enhance bonding properties. So we perform the biology where the formation of hydrogen bonding and borate ester bonds are characterized by FTIR. As mentioned before, the purpose of KULeuven is to enhance the mechanical properties. So here, we performed the rheology test and the compression test to characterize the mechanical properties. Here, we can see the results from the rheology measurement. The G prime storage modulus increase with the angular frequency. That means the G prime was frequency dependent on we can reasonably confirm that the presence of reversible borate ester bonds, because for chemically cross-linked hydrogels, the storage modulus is normally stable. That means it's frequency independent. So here we confirm the presence of reversible bonds. And also, we show the phase angle with the angular frequency. And we see the phase angle as 45. And we calculate the relaxation time of each sample. And let's see that a higher KULeuven content give us a higher relaxation time. That means the physical network is more stronger than the pristine hydrogels. And afterwards, we performed the compression test on the hydrogels, and we noticed that the higher KULeuven content can provide a higher compression strength. So with both of the measurements, we confirmed that the introduce of KULeuven indeed increase the mechanical property and give a stronger physical network. Afterwards, we checked the self-healing properties of the hydrogels. So first, we observe the self-healing by fusion test. Specifically, we dye the hydrogels, cut them, and rejoin. And maybe after some minutes, we stretch the hydrogels, and we notice the hydrogel could be stretched, and we observe that the demonstrate the self-healing process of the hydrogels. And then we continue to observe the self-healing process by optical microscopy, and we see the interface fusion together with time goes. So in this way, we observe the self-healing process of the hydrogels. Afterwards, we quantified the self-healing efficiency by evaluating the resistance change. Specifically, we break the hydrogel first and then recontact them. And after maybe seconds or minutes, the hydrogels self-heal, and we can observe the resistance come back to the initial value. And we calculate the self-healing efficiency by estimating the healing, by estimating the resistance recovery. And we notice that the self-healing efficiency reached up to 1% higher in terms of resistance value. So we can found that our hydrogel sensor is self-healable at room temperature without external stimuli. Because of the existence of borate ions and sodium ions, the hydrogels could be conductive. So we measured the ionic conductivity by electrochemical impedance spectroscopy. As we can see in this figure, we go to the Nyquist plots, and the plots have an intercept with x value. And this value is considered as the bulk resistance of the hydrogels. We extract this value and calculate the ionic conductivity as shown in figure B. And we notice that the pristine hydrogel has a conductivity around 0.31 Siemens per meter. And if we introduce the PULeuven, it didn't change a lot the ionic conductivity and maintains the close value. And this value is sufficient for the wearable sensors. So based on the conductivity and the self-healing ability, and also with the mechanical property, we assemble the hydrogels into wearable sensors. Here, we showcase the strain sensing property. Specifically, we connected the hydrogels with a mechanical tester and also with a potential stat, and then stretch the hydrogels, and we go to the electrical signal chains versus the tensile stream. As we can see here, we can go the curve and then we fit the curve. The strain sensitivity is defined as the slope of the curve. So after fitting, we go to the sensitivity of 2.74. This value exceeds some similar works. And based on the high sensitivity, we encapsulate the hydrogels with some plastic film and attach on the human body. Here we showcase the application like finger slow bending, finger quick bending, wrist down and wrist up. And we noticed that the hydrogel sensor could output reproducible and distinguishable electric signals when monitoring human motion. So we envision that the hydrogel sensor have potential application as a wearable strain sensor. So because the existence of ions in the hydrogels, the movement of ions is sensitive to the temperature changing. So that means our hydrogel sensor may have potential application in temperature sensing. Here, we first measured the temperature coefficient of resistance. This is indexed to evaluate the temperature sensitivity. As we can see that the hydrogel sensor has a negative TCR value. That means the resistance will be decreased if we increase the temperature temperature. With this principle, we assemble the hydrogel as a temperature sensor and switch the hydrogel sensor under different temperature from 0 to 98 and also 40 degrees. And we notice that the hydrogel sensor can produce switchable electrical signals when switching the temperature. Besides, we attach the hydrogel sensor on a beaker and then we fill the hot water. We notice that the hydrogel sensor could produce distinguishable electrical signals when we fill different temperature water. That means if we the high temperature will make the ions more movable and produce a less resistance change. And also, we remove the hydrogel sensor and approach the hydrogel to the hot beaker. And similar like we did before, the hydrogel sensor also produce some different electrical signals. So in this way, we can detect the temperature variation in contact or non-contact mode. Afterwards, we checked the humidity sensing ability. Specifically, we put the hydrogel in wet air environment and dry air environment, and we noticed that the hydrogel are sensitive to the humidity change. If we put it at a wet temperature, the hydrogel may swell and the pathway for the ion conduction will become large. So we can get a different electrical signal change in wet air and dry air. So with this, we attach the hydrogels on mask and monitor the breath process. As we can see, for exhale and inhale process, we can observe electrical signal change. So in this way, our hydrogel sensor may be used as sensors to provide information when breaks up, and simulations here's information collection in a non-contact way. And at last, let's move on to the conclusions of this work. So first, we prepare PA program borax conductive hydrogels by introducing reversible Boris-East bonds and hydrogen bonds. Second, because of the existence of reversible bonds, the hydrogels are self-healable, and this self-healing ability could be realized just within 15 minutes. Third, because of the careful selection of the materials, all hydrogels could keep the high optical transparency in the visible light range. And at last, we envision the hydrogel with multi-sensing capabilities, including strain sensing, temperature sensing, and also with humidity sensing, where this work has been published now. And if you are interested in more information, you can scan this code. At last, I want to express my thank you to my promoter, Professor Pedro Fadim, and co-promoter Irina Torino. Also, a thank you to my PhD committee members, Professor Francisco Molina Lopes and Professor Yuren Lamiton. Also, a big thanks to my amazing collaborators.